It's not going to be a very technical presentation here today. It's just that we, well, first introduce myself. I'm Richard Cantin with SIMCO. That's an easy one. The presentation is going to be about playing around with variability parameters for, so how much it can affect the results, the kind of uncertainty we may have on the different parameters that we considered in probabilistic calculations for service life evaluations. So I just took a structure. It's not a case study. It's a structure. It's a typical structure that can be identified as a marine structure somewhere in the Pacific Ocean, let's say. And we played, so I'm going to talk about that structure a little bit, the model, the variables that we take into account, and all different cases where we blend the different possibilities of variability factors, coefficients of variations, so and how it impacts the results. So that's the plan. The structure that we'll talk about here, as I said, it might be a real structure, but that's not what I considered. So there are no pictures, there are no drawings, but it looks like what you may have here on the right-hand side. It's a marine structure. It looks very much like a UFGS project, for those who are familiar with that. So the service life would be around 75 years. We have three different elements. We have a pile that would be in tidal conditions, a cap that would be in splash zone conditions, and a deck that would be exposed to atmospheric conditions. So these different conditions do not give the same reaction or behavior, and that's what we will see. What's the influence or the sensitivity to the variability. The salinity is assumed at 35 ppt, which is something normal, standard, and the temperature is 25 degrees plus or minus 3. So as I said, it could be something, it's not very variable. I didn't play with that for the purpose of that presentation. It would be something, as I said, this is what you would get in Hawaii, for example. So I'm not saying the structure is in Pearl Harbor, but it could be, or it could be around elsewhere, but these kind of conditions. And the relative humidity varies from 70 to 100%. So 100% is when it's fully submerged. 70% is the ambient humidity. The model that was used is Stadium, which is it's a finite element model. So instead of, well, I'm not going to describe the model here, but it's predictive. So instead of reproducing chloride profiles, we use the real data from the mix, from the binders, the geometry of the structure, and the exposure conditions, and we recreate what would be the chloride profile. Of course, normally it's validated with real chloride profiles, but the idea here is to just to show what we can get with that type of model. There's a probabilistic and deterministic version from that model. We're going to use a probabilistic one, but the average of the probabilistic gives something that looks like the deterministic values. So it's both carried out simultaneously, and you see the results from both. The probabilistic variables that were considered, that I played around, were first the transport properties. So in that model, we have three different transport properties. The first one is the one maybe you're more familiar with, the diffusion coefficient. In that case, it's the ionic diffusion coefficient. So it's measured, it's a property of the material, it's a property of the porous network, measured with a migration test. The volume of permeable voids, that's measured with a standard test. The permeability, well, I should say there's a drying test that was performed, and we get the permeability and the saturation at 50% relative humidity. So based on these data, we can reproduce the humidity a moisture transport within the concrete. That might be useful for unsaturated conditions. Also, the salinity is considered as a variable, the cover, and the corrosion initiation threshold. So all these probabilistic variables are blended together to evaluate a global probability of corrosion initiation at bar depth. The different cases that we look at, we have a standard concrete with a 0.4 water binder ratio, so nothing special here, something that would be considered compliant for most structures like that. In many cases, it might be a bit better, but this is a standard concrete, 25% fly ash, class F. So the properties of that concrete were derived from what we have in the database, and these are standard properties for a mix like that. What's interesting here is the variability of transport properties. These values, so the percentages you see there are the coefficients of variation of the different parameters that were taken into account in the calculations that I'm going to show. And these results come from research. So they were assessed previously a couple of years ago. Sorry, I forgot to bring the reference here, but it's in a peer-reviewed paper somewhere. And if you need it, I can send it. Just reach out after the presentation or send me an email. I can get it to you. But this is the bracket of values that we can take into account for these different parameters. The volume of permeable voids at 5%, I just have one number because that's something that doesn't vary a lot. So 5% is a high variation. It can be 3, 4. I decided just to use one number to limit the number of calculations and possibilities. The diffusion coefficient, it varies either with a coefficient of variation of 8% or 15%. Permeability, I've selected 10 or 20, which are normally, it represents the range of possibilities that we may have for different concretes for those values. The salinity, normally for seawater, these values are super high, but that's something, for the seawater itself, it doesn't vary very much. I still consider the variability just for the purpose of the presentation, but that kind of variability, you may have it more for the atmospheric exposure, where you have airborne chlorides that can vary with the distance from the water, the winds, and so on. So I'm considering that mainly for this type of exposure. The cover, it follows a normal distribution with a value of 75. 75 it's a standard value that we see on many projects. I also took into account 50. I'm going to show you the results that we get with both. So 70 was used for 75 for the piles and caps. 50 was used for the cap and deck. So the deck has a shallower cover. So the more severe the exposure, the higher the cover, of course. The threshold, I used the one in FIB Bolton 34 for probabilistic modeling, which is it's the typical curve with the beta distribution, 0.6 average, 0.2 lower limit, 2% higher limit. I'm not going to discuss the validity of these results here, but that's something that people can refer to, and that's widely used, so I just took that value. It looks like that, by the way. So if you have, it's a curve, the curve, the parameters you have earlier give a threshold distribution like that. And the cover, you have a distribution that may look like that. For the, using the ACI 117 tolerances for the dimensions of the piles that I used and the pile cap, it would be a tolerance of 13 millimeters. For the deck, it would be 10 because it's a thinner element. It's not. It's less than 300 millimeters. And for the purpose of those calculations, I've decided that all the bars would be within tolerance, which is not necessarily the case in practice. Sometimes there's a 95% factor, but I use tolerances that assume that both boundaries of the tolerance interval were reached with a criterion of 10 minus 5 probability. So that gives a tolerance that's mostly within a distribution that's mostly within the acceptable tolerance. Overall, we have where's the okay here. So overall, we have 24 different cases here that I'm going to show. We have those three elements: the piles, the caps, the deck. The exposure, the pile, as I said, it's always in the tidal zone. The cap is always in the splash zone. The deck is always in the atmospheric zone. It's the same concrete in all cases. The volume of permeable void, it's set at 5% in all cases. And then the diffusion coefficient, which is called DOH in stadium, but that's the diffusion coefficient actually. The variability may be 8 or 15. The permeability may be 10 or 20, and the salinity, the variability may be 10 or 20. So, and the cover it's only one value. As I said, for that one here, I tried 50 also. I'll show it later. Threshold, we have one distribution. So blending all this together, we have those 24 different cases, and it's expressed in terms of probability or reliability index. I'm going to show you a bit later. So the reliability index, generally for corrosion, we use, this is based on the centered standard normal distribution. If you draw the S-curve, you'll find that for 90% or the 10% probability of corrosion or 90% safe interval, you have a 1.3 reliability index. It's not exactly 1.3. I think it's 1.28 or something like that, but it's very close. And this would be for structures that can be inspected and repaired over their service life, not necessarily structures that are not accessible. So that's quite a standard value that we see in specifications. So now going to the results, what's interesting for the piles. You see, so this is the probability of corrosion initiation. This is the number of years and how the probability increases based on the different possible conditions that we have that are all determined. The differences are the variability that was assessed or that was attributed to the different transport properties, the diffusion and permeability, and also on the salinity. We have just 4 curves. 1 and 3 overlap, 2, 4, 5, 7, 6, and 8. That means that this one here overlaps this one, and so on. So both curves with a 10% variability overlap, and so on. So what it means is that the fact we have 4 curves for that element, the piles, in the tidal zone that is mostly wet all the time, the permeability doesn't play a big role. So I actually curves, I could have just had 1, 2, 5, and 6, and it would have given the same thing. So you see here 1 is 8, 10. 3 is 8. So when I have 8 and 8, it's the same thing. 10 and 20 doesn't make any difference, and so on. So in that case, it makes a difference changing the salinity. It makes a difference changing the diffusion coefficient. But in a wet environment, the permeability doesn't change much. or so the variability that is attributed to that parameter doesn't affect much the end result. Now the cap, with a cover, a 75 millimeter for a pile cap like that, with that concrete in a splash zone, I have 0. For all these cases, no matter what I decide, or the variability that's attributed to the transport properties, I end up with 0. So not only it's high enough, it could be reduced. And first thing I was wondering is, okay, did we calculate something or not? Why do we have 0? Why do we have the same values? And if you look at the reliability index, and these numbers here are a bit ridiculous but that's what we calculate, but the reliability index starts to be representative maybe in this area here. But we see, it's just to show you that don't necessarily use those numbers, because these represent different interpretations of 0%. It's just the number of digits after the decimal changes. But we did calculate something. It's just that we really have a very low probability of corrosion, and it can be assumed as 0. If we do the same thing here, still for the cap, but reducing the cover to 50, we do see something. So we have a probability of corrosion initiation that increases a little bit. Here, just be careful, because I reduced the scale to 10 instead of 100 as we had earlier, so it stops at 10%. It's just to magnify the scale so we see the differences. And 50 millimeters of cover would be enough in that specific case. It could be decreased even more if we set the target at 10%, which is normally the case. And we see that we have little bit of a higher probability of corrosion for 14, the case 14 here, and case 16. These are the ones with the highest variability on the diffusion coefficient and the salinity. So might be expected, but if I increase the variability of my diffusion coefficient and of the salinity of the water, I may get a higher probability of corrosion. But you see, in the range where we are now, yes, it's higher, but not much, and it doesn't affect the end result. That if I have to assess, and by the way, 50 millimeters is the minimum if I follow the codes, but I could use less than that based on those calculation results. But I just decided to limit it to 50. I haven't tried 30 or 40, but we could afford a little bit a higher probability of corrosion here. So that's interesting. So we have a higher impact in that specific condition of the diffusion and salinity. Last one here is for the deck. It's basically the same thing as with the pile cap. So the deck, that is, I repeat, under atmospheric conditions, probability of corrosion 0 with a 50 millimeter cover. So it's more than enough. It could be reduced, but it would not follow the standards. But if we can assess a cover based on probabilistic modeling, we could use a lower value, and it's shown by the 0 values that we have here. And it's shown by, if I show the reliability index, yes, there's a differentiation between all calculations, but it's still in the range where it's 10 minus hundreds. So it can be considered as a 0. And the last one I want to show you is if we consider the deterministic calculations. So these would be, for each case, the average. And that's the profile we get, the predicted profile at 75 years. We have here, I've drawn a deterministic threshold that would be around, that threshold is selected arbitrarily and it accounts for a safety factor, but generally it's within the bracket of 0.2, 0.7% of the binder content. 0.3 is around the lower end of the interval, so it may be too safe, but it's a safe value. So what we would get with those deterministic values compared to probabilistic, I think it's comparable. So you see the green curve here is for the deck. So the intersection between the chloride content, the profile, and the corrosion initiation threshold, it occurs, it's at 75 years, we're not even close to the cover of 50 millimeters. So yes, we may have corrosion initiation, but for bars that would be below about 22, 25 millimeters from the surface. Deeper than that, it would be okay. We're very close if we put the bars at 50 millimeters for the cap, but we still don't have corrosion. And in that case, I may be close because I set the threshold at 0.3%. If I have used 0.2, for example, it would be different. But we're in that region. So 75 millimeters is a bit safer for the cap. For the pile, the probabilistic calculations were showing that we had corrosion initiation, a high probability. If we use the deterministic approach, we see that the intersection is well past the intersection of the threshold and the cover. So yes, it says also that we should have corrosion at 75 years. And if we compare both, it gives comparable results. Just a word here about the probabilistic calculations and versus deterministic. We shouldn't get different results, and we don't get different results. So with the probabilistic evaluation, I would get for the piles 44, 49. Okay, sorry, you don't see here is that with the model, I can get these curves at any age. So I can see exactly where I'm crossing the intersection here and at which age I have that same curve. So that's how these results were found here. So it's 44, 49 years for the probabilistic calculation. So I would have a service life around that. If I use a deterministic approach, I would have 41. So that's not much different. I think it's of the same order. For the cap and the deck, of course, it's well above 75 years, sorry, with the cover of 75 millimeters. So I don't have the exact values. I didn't extend the calculations to 200 years or 300 years, but it's coherent. That's the message here. So we're not, modeling doesn't give all kinds of results all over the place. You can get something that's quite accurate. And finally, so yes, we were able to determine a required cover in each case. So these calculations can be used for that. Instead of using the codes, we could use the calculations to determine the exact required cover. We are accounting for uncertainty of the probabilistic parameters, and it doesn't affect significantly the calculation results. So if we don't know the exact uncertainty about our transport parameters, we can use values that are documented from other projects, and we won't end up with a prediction that's totally false or totally, not in the right ballpark. So that's another finding that we had here. We can have similar results with probabilistic and deterministic calculations, depending on the corrosion initiation threshold we select. So these are based on experience, based on the conditions, based on there are a lot of things that can influence the corrosion initiation threshold, but I think we can end up with similar results if we select the right values. And we need also to have take care of selecting the right calculation parameters. This is what has the greatest influence, not necessarily the variability, but the exact determination of what we put in the calculations. So that's the key point, the importance of determining the right parameters. So if we have access to test results, it's always better than guessing what we should have with a certain concrete made with certain proportions or ingredients. That's it. So that's it. And if you have questions, my email is there, so just feel free to reach out.